Flux density homework, problem 4. We got a uniform volume charge density of 80 microcoulombs present to the region that goes from 8 millimeters, smaller than radius, smaller than 10 millimeters. And we will consider that the volume charge density is going to be 0 if we are working with radius smaller than 8 millimeters, and that means between 0 and 8 millimeters. So to simplify the problem, let's consider that we got an spheric structure center at the origin. Something like this: C, X, and Y. That means we will have two concentric spheres like this one. For conveniences on the analysis and to make it a little bit more clear, let's make a cut. We will cut on the CY plane and we are going to see X from the front. That means we'll get something like this, and my X looks like a point in here. So the problems tell me we will have a charge, volumetric charge density of 80 microcoulombs per cubic meters between radius of 8 millimeters and 10 millimeters. That means between this point, 8 millimeters, and this point, 10 millimeters. If we are working within these two positions, we will get a charge distribution like this, like that. If we're working in a smaller radius, for example, in here, our charge distribution is going to be 0. If we're working with higher radius than 10 millimeters, we're going to have a charge distribution of 0 again. So the problem is asking me to find the total charge inside a spheric surface with radius equals to 10 millimeters, and also find the flux density at a surface of radius equals to 10 millimeters. Finally, considering that there is no charge for the radius bigger than 10 millimeters, that means this situation, let's find the flux density at a radius of 20 millimeters. Let's go for the first part. We're talking about a sphere that has a surface of radius 10. That means a sphere that covers the whole region where we have the 80 microns per cubic meters. That means all the region that we got a numeric rho b. So in order to get the total charge, we have to make a volumetric integration of rho b dv. Remember, dv for spheric, geometry is going to be radius squared, sine of theta, d theta, d phi. So we just replace this value here. Radius squared, sine of theta, d radius, oh, I'm missing the radius, d radius, d theta, d phi. We're going to integrate from the radius from 0.008, that means 8 millimeters, to a radius of 10 millimeters, 0.01 for radius. For theta, we're going to integrate from 0 to pi, and for phi, we're going to integrate from 0 on to pi. Finally, we replace the value of rho b for that region, which is going to be 80 times 10 at minus 6 because we're working with microcoulombs. That 80 times 10 at minus 6, it's a fixed value, so it can go out of the equation. Q equals 80 times 10 at minus 6. And now, we already know some of these integrals. T phi integrated from 0 to 2 pi will actually deliver phi evaluated from 0 on 2 pi. Sine of theta d theta evaluated from 0 to pi is going to deliver minus cosine of theta 0 to pi. And we will have the integration from 0.008 to 0.01 of radius squared dr. I know phi evaluated from 0 to 2 pi is going to be 2 pi. I know minus cosine of theta evaluated from 0 to pi is going to be 2. And we know what's the result for this integral. So at the end, we'll get that q equals to 80 times 10 at minus 6 times 2 pi times 2 times radius cubed over 3, 0.008 to 0.01. If that's the case, we'll get a charge enclosed of 35.6 nanocoulombs. That's the total charge in this like hollow sphere structure. The result for part A, or the first part. Then we want to calculate the flux density at a radius of 10 millimeters. For that matters, we will only need the charge that we just calculated, and we will apply the Gauss law. Flux density that comes from flux equal to charge equals to closed surface integration of d times ds. Now, for a surface and spheric coordinates, ds equals to radius squared sine of theta d theta d phi. So we will get double integration of d, which we don't know the value, ds radius squared sine of theta d theta d phi. Evaluated theta from 0 to pi, phi 0 on 2 pi. And we have a specific value for the radius, which is 10 millimeters. So we can just replace, oh well, let's just leave it like that and replace at the end. So we'll start solving this equation. D can go out of the equation and radius as well, since we don't have any differential radius. That means d radius squared, and once again, the integration of d phi from 0 to 2 is going to be phi from 0 on 2 pi. The integration of sine of theta d theta from 0 to pi is going to give me minus cosine of theta from 0 to pi. This becomes 2 pi. This becomes 2. That means we will have d radius squared 4 pi equals to my charge. This will just be a matter of solving for d. Let's erase what we got in here. Erase this part. Let's just solve for the value of d. Now solving for d will give me the d equals to charge over radius squared 4 pi. If we know that the q is going to be 35.6 nanocoulombs, coulombs per square meter. For the part B, we replace when radius equals 10 millimeters. That means 0.01 meters. So D is going to be 35.6 times 10 at minus 9 over 0.01 squared or 5. If we replace that value, that would give us 28.39 microcoulombs per square meter. That's the answer for B. Now, for C, we'll consider that radius equals 20 millimeters or 0.02 millimeters. Now, what is important to note? We're working with a radius that extends from here to here. Radius equal 20 millimeters. Even if we extend the radius, the only charge present is the one in this hollow sphere. So it will not affect the calculation of Q. At the end, we will only have to replace the new radius in the flux density equation. So 35.6 times 10 at minus 9 over 0.02 squared for pi. That would deliver 7.098 microcoulombs per square meter. And that would be the answer for the part C.